Hello, Mom over here, and welcome to another lecture video on the history of the atom. For our learning objective, we will summarize the historical development of atom and will organize these ideas into a timeline. Now, I hope the concepts that I will be showing you today or discussing for you today are familiar. So this will be a quick video since we will be reviewing these concepts. Now, the first concept that we will be reviewing is the atomic theory. So as you know, all things or all matter are made up of atoms. Atoms are defined as little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. Now, these are the words of Richard Feynman, one of the physics Nobel laureate. Now, of course, there are more nuances to how atoms behave towards one another, depending on the element, their charges, and so on. But as a general gist, this is a good idea to introduce someone to the concept of an atom. Now, Richard Feynman's idea on atom is of course a modern take. How about historically? So today we will be going over on the ideas of how atom or the idea of atom evolved over time. This is also a good way to see or learn about the philosophy of science, that when it comes to learning about the truth, nothing is constant. As long as new information arises from experimentation and data, scientists should be able to accept new paradigms and be open to new ideas. And that has been reflected specifically to the history of the atom. Now, to go over that, let's start from the very beginning. So, from the very beginning, the concept of matter has been studied by the prevailing ideas in the Greek philosophy. Now, Aristotle is the proponent of the continuous model, wherein he states matter is continuous and can be infinitely divided. Of course, this was also highly influenced by their religion at the time, wherein matter is the elements or the formation of gods. Now, that has been the prevalent model for 2,200 years, and since Aristotle had some influence about him, the most likely people followed his philosophy. Now, take note, we call this a philosophy because there's no experimentation or rational logicism towards his idea, mostly a philosophy. Now, against that philosophy is Democritus, because according to Democritus, matter is made up of indivisible, tiny particles called atomos, literally meaning indivisible in Greek. Now, even if Democritus' philosophy is more correct than that of Aristotle, Aristotle's idea had been the most prevalent until until John Dalton. Now, John Dalton has proposed the billiard ball model. He was the first one to reinstate the idea of Democritus during the modern philosophy or modern physics rather. Now, according to John Dalton, atoms are hard, featureless, indivisible spheres of uniform density. Now, if we try to inspect or try to criticize the sentence, of course, we would have some irregularities because we already have an idea of what atoms are. But for him, it's quite simple. Like when he's talking about atoms, everything is uniform. So regardless of the element, atoms will be identical in their composition and they will just behave differently depending on what type of element they are. And when you combine these different elements, then therefore you make compounds, which is actually correct. When you combine elements together, you make molecules and compounds, but atoms are not physically hard and they're not physically featureless. They are still somewhat like spheres. However, they still have distinct characteristics to them depending on the element. But of course, that concept will be discovered much later. For now, in the 1800s, the scientists worked with the concept of billiard model to understand what atoms are. Now, that concept was challenged 100 years later. 100 years later comes J.J. Thompson with his plum pudding model. Now, of course, plum pudding is a very rare delicacy here in the Philippines. So just imagine it like a raisin bread, okay? With the raisins being the electrons within the atom. Now, the plum pudding model has been proposed because Thomson discovered that electrons exist within each atom during his experiment with the cathode ray tube. His experiment was back in 1897, but the formal model was not proposed until 1904. Now, in his experiment, he observed that there are movements of negatively charged particles through his experimental tube, and regardless of whichever element he's using. Now, originally, he was using gases in studying the particles. What he used to do is bombard the element in order to rip apart the particles within the atom. Now, in that design, he was able to discover that there are particles within the atoms that are negatively charged, like plums in a pudding. At least that's how he described it. Now, if you want to see how the experiment looked like, this is the cathode ray tube that John Dalton had designed before, or rather J.J. Thomson has designed before. So he was able to beam electrons through the tube. Here you can see the tube in our picture A, and the fluorescent strip is the movement of electrons. Now, in order to study the particles that are moving through the tube, he used a magnetic bar. So this is the bar. It will have, of course, a negative and a positive pole. Now, if you can see in picture B, the fluorescent line is deflected downward because it's being attracted by the positive pole of the magnet. On the other hand, the negative pole of the magnet is deflecting the beam the other way, or repelling it, because they are both negatively charged. So that gave J.J. Thomson the idea that whatever particles that are moving in the cathode ray tube are actually negatively charged due to how they behaved when they interacted with the magnetic bar. But of course, J.J. Thomson's understanding of the atom is still incomplete because not only electrons are present, there are more particles found within the atom itself. Now here comes Ernest Rutherford in 1911 with his nuclear model. He figured out that most of the atom is composed of empty space with some positive particles found in the middle. Now, he realized this by using alpha particles. Alpha particles are made up of nucleus of a helium. So he combined a lot of he collected a lot of alpha particles together and used that in order to push it through a gold foil. Now, gold, of course, is a bigger atom. Therefore, the helium nucleus was able to go through. Although some was deflected, most of it was passing through. Now, this gave him an idea that atoms actually have spaces within, but have a concentrated mass in the middle, and that's what he called the nucleus. Now, to give you a better understanding of the Rutherford's alpha scatter experiment, so again, you have your alpha particle source. The alpha particles are just the nuclei of multiple helium atoms. Now, he took the alpha particles and struck it through a gold foil. Now, some of it was deflected because they hit the nucleus of the gold particle. Now remember, since the alpha particles are nuclei, they are positively charged and they will repel or bounce back whenever they hit the nucleus of the gold foil atoms. Next, some of the gold or the alpha particles went through the gold foil because they just went through the empty space that is within the atom itself. Now let us compare the three models of the atom that we have discussed so far, starting with billiard ball model of Dalton. So again, billiard ball model shows that the atom does not have any distinct characteristic regardless of the element and are instead perfectly round spheres. The plum pudding model or the Thompson model has integrated the presence of the negative and positively charged particles, but in J.J. Thomson's time, mostly the presence of negative particles called electrons, while Rutherford's nuclear model has proposed the existence of a positively charged nucleus within. Now, of course, the story is not over because there are still more to discover about the atoms. Here comes Niels Bohr in 1913 with his planetary model. Now, he had specified that existence of electrons is not simply embedded around the atom itself. Instead, electrons move in specific orbits which contain specific energies and allow specific sizes. Now, that is relatively true compared to the previous models that are shown so far. Niels Bohr have specified that when electrons move around the nucleus, they move around it like planets, wherein they have specific orbits. You have level 1, level 2, and level 3, with level 1 being the closest to the nucleus, while level 3 or so forth will be the one with the farthest from the nucleus. Now, Niels Bohr has also proposed that the outer level determines the chemical property of the elements, which has some inkling of truth to it because bonds are possible because of the outer orbit or orbital of the atom. But that is not clarified until the quantum or electron cloud model by Erwin Schrodinger. Now, he proposed in 1926 that electrons do not follow a specific orbit or a predetermined path as shown by Bohr. Instead, electrons move as waves. So electrons can act as both particles and waves and can be described by quantum mechanical equations. So this is where Schrodinger's quantum wave formula comes in. Now, he was able to calculate the proximate space where electrons can be found, and that is called the orbitals. Now, the orbitals is the space in the atom where electrons is most likely to be found. Now, take note, since we are working with quantum particles, the possibilities now are not 100% because electrons move around the atom constantly and there is no way to be 100% sure where the electron would be within the atom. Instead, it's best to describe it that orbitals are spaces wherein electrons will be most likely to be found. Now, the different elements will have different orbitals. The bigger the element are, the more orbital spaces can be found within the atom itself. And alright, that should complete the different versions of the atomic model, starting with the very simple billiard ball model by John Dalton, followed by the plum pudding model by J.J. Thomson, which has incorporated the presence of electrons, followed by Ernest Rutherford, which has identified the presence of positive, positively charged particles in the nucleus, the planetary orbit by Niels Bohr, which specified that electrons move in specific orbits, while Erwin Schrödinger clarified that it's not orbits but instead orbitals, where electrons constantly move within the atom and they have spaces wherein they can be most likely found. Now, of course, the last example or the last model by Erwin Schrödinger is still incomplete, but will be later be completed by James Chadwick in 1932. So he proved using a similar experiment by Rutherford that neutrons are present in the nucleus of the atoms itself, which completes now our very own understanding of the atom. Now, our modern understanding of the atomic model is a combination of the efforts of scientists from hundreds of years ago. So again, we have different particles within the atoms, namely the protons and neutrons and the electrons. The protons are the positively charged particles found within the middle of the of the nucleus rather, combined with neutrons which are neutrally charged, which together, the protons and the neutrons, make the nucleus of the atom. And the electron cloud shows us the likelihood of where the electrons can be. Now, the electron cloud again does not show how many electrons there are, it just shows where the electrons are moving and where most likely they will be found. Now, because of that, we can now study the differences between the elements. And as you know, the changes in the electrons, protons, and neutrons will dictate what type of element there will be in the matter itself. So for example, you have carbon. The atomic number of carbon is 6. The atomic number, by the way, is the number of protons found within the nucleus. Next, the atomic mass will be the mass of the atom itself. So technically, that would be the mass of the neutron and the protons together. And it's expressed in atomic mass units or AMU. So whenever you take a look at the periodic table, usually the bigger number is the atomic mass because it's a combination of the protons and neutrons mass, while the atomic number is specifically the number of protons only. Now, I hope that short historical perspective on the development of the history of the atom gave you a better appreciation of the periodic table of elements. So remember, our periodic table of elements is organized by atomic number, and that atomic number is equal to the amount or number of protons found within the nucleus. With the periodic table, you will also see the atomic mass unit, which is composed of the mass of the protons and the mass of the neutrons within the nucleus. Not to mention, there are also variations in terms of electron number. So the electrons, of course, are still moving around the atomic nucleus and can vary sometimes depending on the isotope. But for now, we'll focus on the neutral elements of the periodic table throughout our discussions. Alright, so that should end my video. If you have any questions, do not hesitate to message me through our communication channels. See you. Bye.